the crowning achievements of modern mathematics, which was to do something. Guys, I'm going to say this because at the time this was proved, nobody had any idea what the nature of the orbits of the planets were, right? They had observations that suggested that planets moved in elliptical orbits that were numerical, and they had a theory of gravity due to Newton. And it took, actually, I think the contemporary versions of this basically believe that Newton is actually not the one that proved Kepler's laws, that it wasn't a rigorous proof, and it was actually one of the Bernoulli brothers who did it. Okay. It doesn't really matter for us, for the history, but like this is it's a big deal. And we were going to do it with a basis of a set of tools to start with the idea of a path. So last time we defined the notion of a path to be a function x that took an interval and mapped it into n-dimensional space. For the purposes of what we're going to do today, we're going to be looking at paths that have this property. Paths that take intervals and map them into R3. We're going to assume that our path is twice differentiable, which is a reasonable physical assumption. If you think about like, oh, well, if things aren't moving in differentiable paths in nature, then like, you know, jaggy corners aren't usually something you see in sort of in motion, right? So we're going to assume that x is twice differentiable. I've mentioned before that twice differentiability is one of the assumptions that shows up all over contemporary math and science. The reason is you really want acceleration to be continuously related to position, right? At least in a piecewise manner, if possible. I'm going to remind you that we're going to make the following notations. We're going to have x as a path. If I take its derivative, I have the velocity vector. So x of t prime is equal to v of t. It's okay to use the prime notation because these are functions of one input variable. So it's regular old derivative. I'm going to denote by v without the hat. That's going to be the speed vector. Make the assumption here that this is a function. Nothing that we're dealing with is constant. Everything is moving. And then we're going to have v prime of t is going to be a of t. Okay. I'm also going to ask you what the universal law of gravitation is. So, all y'all been around Bush for a while. What's the universal law of gravitation? No physics majors are allowed to answer this question. No, that's the actual amount of acceleration. Okay. F, vector quantity F. We're living in the three-dimensional world now where things actually point in directions, right? So the gravitational force between two objects is minus, I heard an M1. So we're not going to use M1 and M2. We're going to use big M and little m. What else do I need here? There's a G in there somewhere, but is it big G or little g? Big G, the universal gravitational constant, capital G. Experimentally determined. What am I missing? I better have a radius squared. What do I mean by r squared down here? I mean the length of the vector that connects the two objects that we're considering. Okay, so we're going to draw a picture where it's clear what I mean by this r. R does not have a hat on it, so it is a magnitude, but r is a function. And then we have some vector u. I'm going to think about this also as being gmm over r cubed, r hash. These are vectors. The idea here is that you have an object of mass m and an object of mass little m. The r vector is the vector that connects them. It is a function of time. As this thing moves, this vector moves. Somebody's casting a spell over there or something. Okay. So the way that we're going to make this, the easiest possible way to compute this stuff is actually, we're going to put the big mass, which is going to be the sun, we're going to put it at the origin of the coordinate system that we're working with. But right, this is the vector version of the universal law of gravitation, is that if you have a vector r, that connects M to a moving object with mass little m, that the force experienced at any event, this itself is a function of time, right? Because if this object is moving in a path that's described by this vector, then the force itself is going to vary. In class, you know, those of you that have done like physics and like high level engineering or have seen versions of this where things have been moving, right? If all you've ever done is sort of high school level physics, this is always a static problem where you're computing like static force in a static situation. So the point of vector calculus is to be able to treat this as a moving system. And that's what we're going to do here. So I want you to remember this is a, oh, I guess I should define here. By u, I mean a position vector divided by the length of the position vector. Okay, so u is a unit vector pointing in the same direction as the position vector. Okay, so the last thing we'll do is we'll set up what this actually looks like. So we're going to make the following sort of coordinate setup here. So we're going to put the first version of this. We're going to put the sun at the origin. There's the sun. And now here, there's going to be some planet moving. There's going to be a planet right there. It's going to be located at position P. And then R is going to be the vector. R of T is going to be the vector. O. So the first thing we want to do is actually, before anything else, it turns out the first move that we make is I have to show that the motion of the planet is planar. So the planet can't be spinning around in 3 dimensions. It has to be the case that our sort of first goal is to show that whatever the planet is doing, that it's moving always in the same plane of motion, right? Because that will let us reduce the problem to just one of the coordinate planes. So step 1 in our setup is going to be to show that this motion of a planet, if the planet is moving and it's subject to the universal law of gravitation, that it has to move in a plane. Make sense? Yep.
Would it always move in a plane?
Well, I mean, that's what's going to happen is we're going to start with a plane that's tipped up, and then we'll just, but without loss of generality, we'll take the coordinate system and rotate it so that we're just in the, I can let the coordinate system be whatever I want, right? As soon as I've got a planet moving in a plane, I'll just make the coordinate system with respect to the plane of motion. Now, I should point out here that in everything that we're going to do, you would be famous, actually. If you want to get famous, thoroughly analyze 4 moving bodies in a gravitational system. Go ahead and do that, and you will be famous, because even the 3 moving body problem is so complicated that it's still not fully solved. So we're doing what's called a 2-body problem, because you can actually write down the solution. In general, the n-body problem is very hard. Because you can imagine if you have even three objects, every object is exerting gravity on every other object in the system, and all of those are evolving as they move, right? So it's incredibly complicated. So we're going to make the massive simplifying assumption that there's a solar system with 2 things in it, a sun in the middle and a planet moving around it. In some sense, Kepler got lucky. Okay, we're going to take as given certain product rules. You guys actually, we did this, we mentioned these in passing. I want you to tell me what you think this is. If I have a vector function x dotted with a vector function y, what should the derivative of the product be? They're functions now. These aren't orthogonal. There's 2 functions. If I gave you this, put this off camera. If I gave you this, what would you do? Product of functions, I take the derivative. What's the rule? What is d by dx of fg? F prime g plus fg prime, right? Product rule of the scalar variables also holds in vector variables. So the product rule for scalar says if you have a product of functions that you take a product rule by doing f prime g plus fg prime. The same rule holds for vector functions over a dot product. Okay, so we went over this a little bit in chapter 1, but the idea here is that d by dt, that this derivative can be gotten by doing dx dt dotted with y plus x dotted with dy dt. It's one of the most useful things about these products is they respect the same calculus transformations that we have for scalar functions, right? The dot product respects the product rule. we're going to be using that. And also, and to me, more surprisingly, it turns out to be the case that the product rule also respects the cross product. So if I take a derivative of cross product, I get the same rule. And that's extra weird. Dx dt crossed with y plus x crossed with dy dt. Okay. So vector products satisfy product rule. Which is another argument for vector calculus, right? It looks like calculus. We want derivatives to do this. Yep.
So the dot product, the dot product and the multiplication, we can interchange.
So there are rules that relate the interchange of operations between dot and cross products. There are identities that let you switch back and forth from dot products to cross products, but they're complicated. Right. So there's not really a natural geometric way of thinking about how these things interact together. I mean, one rule that's well, I'll point out whenever we're going to use anything involving mixtures of dots and cross products, I'll point them out. They're not usually worth taking the time to prove. They're just the sort of computational tools that are nice to know exist. There's a lot of identities involving mixtures of cross products and dot products that are proved just by calculating giant formulas and showing that they're equal to each other. Not really a lot of geometry involved, just a whole lot of grinding. Okay. Okay. Okay, so here's claim one. Let the velocity vector be equal to the derivative of the position vector. So B is our prime of t. I guess maybe over here I'll put our picture. I want you to imagine this is the planet P. This is the sun at the origin. We've got the vector r right here, and r prime. This is changing with respect to time, so this is moving, and we're going to take the derivative. Okay. So here's claim one. R cross V is C, where C is a constant. So even though R and V are functions that are moving, this is the position vector, this is the velocity vector. My claim is that the vector, a vector perpendicular to them, is a constant vector. So what would that mean? Well, if R cross V always have the same vector that is perpendicular to them, both, then that means they must live in a plane and never leave it, right? The velocity vector always and the position vector are always lying in the same plane because they have the same normal. We think about this as being the normal vector to the plane containing motion. So if I could show that this was true, this would force R to be lying in one plane of motion. Does that make sense? The idea here is that if you had R and you have V, and no matter where in the, so you can think about V as sort of sticking out of the path. If you have R and V at always the same vector, there's a constant vector that's always perpendicular to that. You can never leave the plane that they're rotating because the plane never changes direction because the normal vector never changes direction. All right? Okay, how do you prove that? D by dt of R cross V. And now we're going to use the vector product rule. So the derivative of this vector is equal to dr dt cross V plus R cross V dt. Oh wait, I know a name for dr dt. It's V. I know a name for dv dt. Hey. Right? What's V cross V equal to? If I have two vectors that point the same direction, what does the cross product do? So I know if I've got two vectors that point different directions, the cross product produces a perpendicular vector. If I give you two vectors that are parallel, what does the dot product or the cross product do? Is there a single normal vector that comes out if I have two vectors pointing the same direction? Cross product fails in that case, and it spits out a 0. So if I have two vectors that point the same direction and I take the cross, I get nothing. Okay. So the reason that we're doing this argument is, one, because there's sort of the cultural thing of having seen why Kepler's laws hold by vector calculus, but two, we're going to be using a bunch of really basic facts about vector calculus and the relationship of vectors to do this direct derivation. Okay. But wait a second. I'm living in a regime where the universal law of gravitation holds. So what I've got right now is this. I have that d by dt of r cross b is equal to r cross a. Yep.
For the product rule involving the cross product,
Yes.
the order matters.
The order very much matters here, yeah.
For unit product.
For the dot product, for real dot products, it doesn't matter, right? So since we're living in a real value universe for this, yeah, you can switch for the vector dot product, you can switch the order to be whatever you want. But for cross, I'm being very careful to try to make sure I maintain the same orientation. Okay, are we good to here? Okay, so what is Newton's law about the relationship between force and acceleration? F equals ma. So the vector F is equal to m times the acceleration vector a, but I know what F is because I know the force that's acting on this object between the universal law of gravitation holds here, right? So this is minus gm little m over let's see, which version do I want here? I want the r cubed version with the r in it. That's the force between the sun and the planet, right? Is equal to m times a. Well, the little m's cancel. That's nice. But what do we get? Minus gm over r cubed r is equal to a. But wait, that means that a, the acceleration, is a constant multiple, or rather a scalar multiple of the vector r. So this derivative is equal to. So we do this computation off to the side. We take this, and what we get is d by dt of r cross b is equal to r cross minus gm over r cubed r. Those vectors point the same direction. What's the cross? 0. Oh, d by dt of r cross b is the 0 vector. Now what? Derivative of this cross is 0. What I wanted to know was about this vector, right? I want to know about this vector. I'm trying to show it's equal to a constant. And what I have is this. That's what I want. And what I've got is that d by dt of r cross b is equal to 0. Is there any way I can use this to get that? Integrate it. You're allowed to integrate a vector function, right? You can integrate a vector function. It's a function of one variable. You just integrate it with a regular old Riemann integral. And if you integrate this, you're going to get that r cross b is equal to not a scalar constant, but a scalar constant in each variable, which is a vector constant. So integrating.
Is that a B or across B?
This is a v. Yeah, sorry, r cross b. So there you go. R cross v is a constant. And notice there's nowhere to be used a particular value of r, right? This holds for all t. This holds. So that means r cross v always points the same direction. And so r moves in a plane. All right, so we're one step towards proving that planets move in ellipses. At least we know they move in a flat way. Sorry, this is supposed to maybe rewrite this so it actually reads like English. R moves in a. how you say plane. So this is actually the first step towards Kepler's first law, which says planets move in ellipses with the sun at one focus. In order to get that, I have to start with the idea that the function or that the planets move in a plane. So if you guys are willing to put up with the fact that planets move in planes, let's take now as proven that a planet in a two-body system orbiting a sun moves in a plane. So what I'm going to do is I'm going to reconfigure the coordinate system now. So since I move in a plane, I can do this. There's Z. We'll have X come out this way. We'll have Y go out this way. Remember, we do this so that we have the right-hand rule making Z point the right direction. So what we're going to do is we're going to imagine that we're just going to set the coordinate system up so that the XY plane is the plane of rotation. Just a coordinate system. It doesn't matter how I set this up. So I'm going to make the assumption now that, again, the sun is at the origin, that the plane or the planet now, P, is rotating in the XY plane. I'm pretending I know it's an ellipse already. I don't. This is just imagine there's some path. I don't know what it's doing. Attached to this path is a vector r, which tells us the position. That's r of t. There's a velocity vector sticking out of that called v of t. R and v are both in the same plane because their cross product in any direction was always equal to c, a scalar that's always the same scalar. Make sense what the setup is?
Is he going up?
C is kind of going, yeah, what you might imagine here is this is the plane, the sun is in the origin, the planet's going around it, and the C vector comes straight up out of it. This is a problem looking at somebody else's drawings. Okay. So what we're going to do is we're going to derive the polar equation for an ellipse. And then we'll show that it's actually an ellipse in the way you guys remember. Actually, does anybody remember what the equation of ellipse is? All y'all and then all these conic sections.
X squared.
X squared. Oh, let's do the actual one with the shifted center.
Over a squared plus y minus a squared over b squared.
All right. So eventually what we're going to do is we're going to derive an equation in polar coordinates, and we're going to show that it reduces one of these. And all along the way, we're going to make a delightful physical observation. Okay. So step one here. I'm going to write down r is equal to little r times u. That makes sense, right? I'm saying that u is the unit vector pointing in the direction of r, and so if I take that unit vector and I multiply it by the speed, or the length of the r vector, I get the actual r vector back out, right? This just comes from the definition that u is equal to r divided by the length of r, and where r is equal to the length of r. That's the notation. Okay. Okay, so v is equal to d by dt of r, which is actually equal to d by dt of ru. It's going to feel kind of like cheating. Because now r is a function of time, and also u is a function of time. So I have to use the product rule here, right? This object is moving. The direction that it's pointing in is moving, and also the length of the vector is moving as well. These are both functions of time. So I can use the regular product rule to write r dt u plus r times dt. Make sense? So I'm just cheating and getting another expression for the velocity vector, basically, right? Kind of what I'm doing here. So if v is equal to this expression, then I can write c is equal to r cross v, which equals ru cross, okay, so r was equal to ru, but I know that v in this language is equal to dr dt u plus r du dt. I haven't done anything. I replaced R with its definition, and I replaced V with this product rule that I've calculated. How does a cross product distribute over addition? Well, it's a product, so it just does, right? If you have a cross product of a sum of vectors, it's the cross of the first two plus the cross of this with this, right? This is the way cross products work. They satisfy a distributive property. So we get, what are we getting out of this? There's an R here. And there's an ER here. Okay, so they're going to cheat. Sorry, I don't know why I did this in my notes. What I'm going to do is this. This and this get crossed together. So we get an R squared U cross du dt. That's this term and this one. Does that make sense? R is a scalar quantity. It's a function, but it's a scalar, so I can pull it out of the cross. Plus R dr dt. You can see we're using the same tricks over and over and over again. What is U cross U? Zero, all that term disappears because U cross U is nothing. So what we conclude is C is equal to R squared U cross du dt. Now there's an interesting fact.
Professor, can you re-explain that cross again?
What I did here?
Yeah.
It's this vector cross this one plus this vector across this one. I mean, I should have kept them in the same order, but I didn't in my notes. It doesn't matter because they're adding A plus B and B plus A are the same thing. Yep.
It's like conservation of momentum related.
In the background. I mean, it just carries through. It basically carries through with the universal law of gravitation. It forces all this stuff.
Yeah, that's going to be like speed and position, right?
Yeah. Yeah, we're not doing all the physical interpretations of all these quantities. We'll do when we start doing the Frenet frames, right? The point here is that when they did this, they had no notion of any of these forces at all, right? They were working with basically nothing, with no machinery other than calculus. They managed to show themselves. Okay. Okay. So here's a weird fact. So it turns out to be the case that if the length of a vector is equal to a constant. So if you have a vector function, it always spits out the same speed, same length, not speed, but same length no matter what you do. It turns out to be the case that the vector and its derivative are orthogonal to each other. If the vector has constant length, then the vector and its derivative are orthogonal. Now there's a sort of there's an argument for this involving inner products, but from a physical standpoint, what I want you to think is if you're always the same length, no matter where you go, then you're trapped on a circle. You're moving in a circle. If your length is always the same, you're moving in a circle. Well, what's your velocity if you're moving in a circle? Always tangent to the radius of the circle, right? So this is true because your velocity and your position are a radius of a circle and a tangent to a circle, which are always perpendicular. So you can prove this mathematically. It's up in the notes what the proof is, but it's just basically using dot products. The physical intuition here is if you're moving on a circle, your velocity is always tangent to the circle. What does this mean in this is? I guess I should point out what I mean here specifically is that x dot dx dt. So we're going to have occasion to use this dot product, right? That if I take something with constant length and I multiply, I mean, yeah, this is going to come up. We're going to have something like dotted with its derivative. It's going to have a constant length, and so we're going to claim that it's equal to 0. So that's how we're going to use this factor. All right, 2. Remember that A is equal to minus GM over R squared U. That was the force of acceleration on this thing. Save this. In case those of you are worried about this, we're going to do one long ass derivation in this entire class. So this is it. But this is a really important application. A cross C is equal to, okay, so if A is equal to this and C is equal to this, then I can write A cross C is equal to minus GM over R squared U cross with R squared U cross du dt. That's A from here. That's C from here. So I've got A cross C.
Is it just crossing with U and not with R?
It's all of this.
It's all of that.
Sorry about the ambiguity in the notation. And that's equal to, after a bunch of algebra, which you can read in the notes if you want, you end up with GM times U cross du dt cross U. So it's like cross products all piled up together. Okay, somebody asked me about relationships between dot products and scalar products. It turns out that if you have A cross B cross C, if you're willing to grind through the computation, you can show that this holds. This is a way of converting multiple cross products into dot products. Can I give you a geometric explanation for why that holds? No. The guys that did this just did it by writing out huge formulas and noticing the relationships. Now, why did they do it? Because that means this quantity, which is a cross product and a cross product, can be turned into this. Yep.
What happened to the negative on the
We actually flipped the order of we flipped this to the front. So see, there's a U cross du on the right and a U on the left in the cross. I flipped that to the front, which killed the negative. A cross B and B cross A are related by a change of sign. How long is the vector U? It's presumed to be a unit vector. That's why I called it U, right? What's the dot product of a unit vector with itself? 1. So this is GM times 1 du dt. Oh, and look, if that has constant length, then I can apply this idea. The dot product of a constant length vector, if it's a unit vector, certainly has constant length, dotted with its derivative. That's the radius tangent relationship on a circle. This is equal to 0. So we just get GM du dt, which I rewrite as d by dt of GM. So all of that computation must have showed that this relationship holds. A cross C is equal to that quantity right there. Those of you that have had dynamics or kinematics or anything in mechanics are sitting here trying to put physical interpretations on all these, which, I mean, they do have physical interpretations. I am trying to keep this as light as I can. A cross C is equal to, also, there's another way of writing A cross C, which is as dV dt cross C. And this is equal to, now here's a pull on the fast one on you. That's the same as dV dt cross C plus V cross. Why is that true? I've just invented a term out of nowhere. Why can I do that? Oh, because dc dt, C is a scalar, so it has a 0 derivative. So basically what I'm trying to do is take this and rewrite it as an application of the product rule, right? So this looks like half of a product rule, but the other half isn't there, right? But if I can put it here, well, these are equal because that's a 0 vector. And so I just add it in. It's like adding, we're high level students here. We can uncancel 0 in a special way if we feel like it. So I just uncancel 0 in that specific way. And then this turns out to be equal to d by dt of V cross C. If you applied this product rule to the cross, it's actually easier to see in this direction. If you started with this quantity and you took its product rule, this is what the product rule would be. But C is a constant vector, so its derivative is nothing. That term disappears and you get this back out the other side. So now what do we have? We have A cross C on the one hand is equal to this. And in the other hand, it's equal to that. And that means d by dt of V cross C, that's one thing A cross C is equal to d by dt of GMU. I should put a little tail on the. Does that make sense? Maybe it doesn't make sense, but at least all we're doing is turning the crank, right? You can imagine it's like 1680 and you're sitting in your room by candlelight, just like mashing vectors together and seeing what happens, right? Because you have no idea what's going on. You just, like, how am I going to turn this into ellipse? These guys were masters at this kind of mathematics. What on earth am I going to do with that? Derivative of something is equal to derivative of something else. I can integrate it, right? I got a derivative on this side. It's just a vector function. I can integrate that. And this is a vector function. I can integrate that. So just integrate both sides. And what do you get? I mean, this is about the easiest kind of differential equation that exists. A derivative is equal to a derivative. So integrate. And what you end up with is dmu plus d is equal to cross C. Why the plus d? It's the constant of integration, right? I mean, if I integrate, like a derivative would destroy a constant. So I have this some arbitrarily scalar vector that shows a constant vector. This is the constant of integration. And I guess the next claim is that how do I know that D has to be in the same plane that all the rest of this is? The claim is that D is also in the XY plane. Why? U, remember, is a multiple of the R vector. And the R vector lies in the XY plane. Remember, the picture at the beginning was we had the XY plane look like this. Here was the vector R, and U is just a unit vector that points in that same direction. Right? And this is V cross C. Well, that has to be in the XY plane because C is perpendicular to the plane that both R and V lie in, and we're crossing it with V, so it better pick up R. So since this is in the XY plane and this is in the XY plane, that also better be in the XY plane. All right. So now rotate the whole system so that the vector D sits on the x-axis. That's right. This is the way physicists do things, man. Engineers, like, I don't know, I don't want to do anything hard. Rotate the system again. Throw the old coordinate system away and make a new coordinate system. So now the picture looks like this. We have a z-axis sticking up. We have the y-axis kind of poking into the back like this. The x-axis we imagine as being here. So I've just taken the system and this is a terrible here. Okay. So again, I just think you imagine we're on the table. And all we're doing is taking our XY system and rotating it so that the x coordinate lies where the D vector is. So I imagine I've got some vector D. The vector R is out here somewhere. And there's an angle between those vectors, theta. D is a fixed vector, right? It was a constant. It's fixed. R is rotating with respect to the vector theta. The whole point of all of this is that every time we integrate, we've gotten these scalar things out that can't move. D is a fixed vector. So since D is fixed, that means I can re-parameterize the problem in terms of the angle that the vector R that describes the motion of the planet is making with this fixed vector D. Is that right? Hopefully. I mean, if D is stuck where it is, I'm just going to do everything relative to D. R is doing whatever it's doing, but D is going to be my new zero. It gives me a way of setting up a notion of angle, is the idea. D is the anchor point I use to define what this angle theta is. All right. So what's this? How can I get theta into the picture? I mean, I've got this theta that's measuring the angle between this fixed vector d and this vector r, but I can use a dot product to do that.
Is it the length of U?
Yeah, there we go. The length of u times the length of d
Times cosine?
times the cosine of the angle between them. But the length of u is 1. So we rewrite this as u dot d is equal to little d. So d without the hat just means the length of d times the cosine of theta. Now we're here. We finally made it. All this grinding vector computation, which you can see is more length in my notes, lands us here. C squared. So C here being the length of C is equal to C dot C. Remember that the length of a vector squared is equal to the vector dotted with itself. The thing we showed. V dot V was equal to the length of V squared. That's what I'm saying here. The length of C squared is equal to C dotted with itself. But that's equal to R cross V dotted with C. And remember, C was the special vector that was the vector that was R cross V. But R cross V dotted with C, I can use the associative property to move the cross and the dot product around each other. So I get R dotted with V cross C. This is the way associativity works with mixed vector products. So if I have a cross and a dot, I can switch the parentheses and I move the position of the dot and the cross. That gets me R, this is equal to RU dotted with, oh, what I know what V cross C is. V cross C is equal to GMU plus D. And that's equal to GMR U dot U plus R U dot D. So more nonsense vector math, just slopping symbols around and hoping things cancel. Oh, but look, I've managed to create another U dot U. U is a unit vector. U dot U dot U is 1. So C squared is equal to GMR, but I know this quantity too, right? U dot D, I just said was D cosine theta. So I get R D cosine theta. So I want you to notice. There's a single variable that's moving in here. In fact, like there's a theta that goes in as an input, and the response to it is in the R, the length of the vector that comes out. What we've done is we've reduced this vector problem into a problem where we've related the input angle and the output length. This is implicitly a polar function. C is constant, G is constant, M is constant, R is just a length, it's not a vector anymore. R is a length, D was constant, and the input is the angle theta. So if I resort this equation, so this is already implicitly R as a function of theta. And if you solve it for R, you get this. So we're going to make the simplifying assumption here that this can be represented by, this is just a scalar. So I'm going to call that P. And this scalar down here, I'm going to call E, which if you know what you're doing, is going to represent the eccentricity of the conic section that we're talking about. This essentially says that R is equal to P over 1 plus E cosine theta. And that, believe it or not, this is a polar conic section. Now, what are the 3 conic sections it could be? And all 3 of these motions show up in the study of planetary objects. What are the conic sections, the basic ones? Hyperbolas, parabolas, and ellipses. Okay. Yeah, so rearranging this using the fact that x is equal to r cosine theta and y is equal to r sine theta, you get the equation 1 minus e squared x squared plus 2p e to the x plus y squared. So you can take this, you can multiply both sides by this denominator and just do a bunch of algebra sorting. This is what falls out when you're done doing that. Just using the relations that look like this. Where does the y come from? It comes from the fact that you're going to end up with an r squared when you do that. So you do a bunch of algebra on this, not a bunch, a couple of lines of algebra, which gives you this equation. Now this pretty clearly looks like a regular old conic section. If this term was not here, you would be talking about a parabola because you'd have x plus y squared. If this term was positive, you have an ellipse because you have something x squared plus something y squared. And if this term was negative, you have a hyperbola. What is the, okay, so those from here, without knowing any, remember, these guys didn't know anything about what E could be, right? How did they decide it was an ellipse? If E is less than 1 in absolute value, you have an ellipse. If E is equal to plus or minus 1, you have a parabola. If the absolute value of E is greater than 1, you have a hyperbola. You are a scientist in the 1680s, and you have to make a decision about how the planets travel. Why did they decide they were ellipses? Because they were still there. Like, you know, as time went on, the planets didn't fly away, right? They kept coming back. They had records of these things being in the sky for centuries. So because they knew the planet stayed in the sky, they just made the assumption, well, if it was a hyperbola, the planets would come in and then they would leave and that would be it, right? Hyperbola wouldn't even get close to the sun. It would go like this, and then whoop, it would just disappear. If it was a parabola, it would wrap around the sun and then disappear. Focus of a parabola is on the inside of the parabola. If, on the other hand, it was an ellipse, the planet would stick around. So they just guessed. I don't know, probably they're ellipses because they've been here for a couple hundred years. So we're just going to assume E is less than 1. There you go. There's your, what I think is a delightful physical observation. Okay. So by observation, the absolute value of E is less than 1 because we know that these things, like, we're going to make the assumption we've got a closed orbit. The things are coming back around again. Now, I mean, it's not a trivial assumption because comets travel on these paths, right? A lot of like objects in the solar system travel on these like non-closed paths or ellipses with high eccentricity. Notice, okay, so what did we actually do to get here? So we're not going to talk about how to get the focus out right now because I don't have time. But what machinery did we actually use to get here? Why is this such a crowning achievement? Remember, they had no idea what the solar system looked like off of planetary observations that was some dude sitting in a dome for 50 years writing down numbers. That's what Brahe did. Brahe just had thousands of pages of numerical observations. Kepler figured out that particular objects that Brahe was writing about were traveling on paths that looked like elliptic, the only numerical interpretation for what they were doing on the basis of nothing, on the basis of the only math they had was conic sections, assumed, I don't know, conic section. And he ended up being able to, you know, with no notion of gravity, Kepler says, planets move in ellipses. And the sun is in an orbit. And about 50 years later, 50 to 100 years later, the construction of vector calculus allowed the sort of early mathematicians to take Kepler's guess about what was happening, which was necessary because if you didn't know what the answer was, you would have no idea how to mash this vector map together, right? Kepler made the observation about what he thought the path was. Newton needed to come up with a theory of gravitation so that somebody could glue the pieces together to show that they forced each other to happen. The gravitational theory required that the planets move in ellipses. Kepler's notion was planets were shooting vectors of energy at the sun. It's the only thing he could come up with was, I don't know, I mean, something's got to be holding it on. So invisible beams of energy that were doing it, which, you know, it's not too far off. He just didn't know what it was, right? The Newton observation, the profound observation of this type of mathematics was the connection between these small scale gravitational things that were being measured on Earth and the big scale stuff that was in astronomy, right? This actually turned, this more than anything else, probably turned gravity into the universal force that got studied intensely over the next period of time. Okay, if you want to see why the sun has to be an ellipse, I would suggest that you read the rest of this argument. It's nothing more than the old, like, putting this in the form x minus h squared over a squared plus y minus k squared over b squared. And it turns out to be the case that when you locate the coordinates of the ellipse, the sun sits at one of the foci, which is a remarkable fact, actually. And again, all of this really just comes down, I mean, it tells you something about like the power of the universal theory of gravitation in the vector formulation. Right? So what we're going to do is the derivations we're going to do in the future aren't going to look as intense as this, but we're going to try to use the same idea of studying dots and crosses of these physical vector quantities to study three-dimensional motion of general objects, not just objects that are controlled by gravitational force. All right, thanks for sitting through the derivation. I hope something is interesting enough, and yeah, I'll see you guys next time.
What's the last one? You say is sun.
The sun is at, sorry,
Also, just to be clear, E is just a constant, right?
E is a constant.
It's not 2.7, whatever.
No. This is E is a constant called the eccentricity.
Gotcha.
Right, eccentricity measures how circular or elliptical an ellipse is. Right, so the closer you are to one, the more circular the distance turns out to be. And the further away, the more like ocular.
And then you just talking about like spaces and complex analysis. Is that like kind of like quantum right now? It's in
Oh, everything
space.
Quantum, yeah. I mean, that's what I am I'm in Hilbert space.
Yeah,
That's what I do. Yeah. So
okay.
complex, infinite dimensional complex vector space is going to be the heart of quantum.
Yeah. Okay. It's interesting. I just keep getting like tidbits around campus of almost.
Can I ask something?
Yeah.
With the time, like,
I'll be in my office 11 tomorrow. I think that's going to try to minimize. Get it in after that.
I could have kind of done quick. So if someone would like want us to do this homework kind of to your office. So when is the deadline? You know, when
I'd like to have it by tomorrow. I'd like to have it tomorrow by the time I hand it to the grader, which would be probably around like sometime between noon and 1 tomorrow. But like if it comes in after that, I'll still be able to get it.
oh, thank you.
Yep.
I have a question.
Sure.